Hello. Today, what I'm going to do is I'm going to start with chapter 4. I hope you're doing well. So I'm going to start by doing some ALEKS problems from chapter 4. There are other videos available for chapter 4, so I'll make those available on YouTube very soon, but this will be there as well. So let's do the following. Let's come over to the first type of problem, and then we'll talk a little bit about it. Okay, so this is from chapter 4. Chapter 4 is concerned with different types of chemical reactions. The first type of chemical reaction that we'll look at is called the precipitation reaction. And precipitation reactions are based on the idea of dissolution, things dissolving. So let's read through the question here and then we'll take a look at it. The names and chemical formula of some chemical compounds are written in the first two columns of the table below. Each compound is soluble in water. Imagine that a few tenths of a mole of each compound is dissolved in a liter of water. Then write down in the third column of the table the chemical formula of the major chemical species that will be present in this solution. For example, you know water itself will be present, right? So you can begin each list with the chemical formula for water, H2O, and note that a major chemical species for those present in concentrations of greater than 10 to the negative 6 moles per liter. We'll talk more about concentration later in the chapter, okay? So if you take a look here, there are 3 substances that are shown there, and what we're asked to do is we're asked to write the chemical formula of the species that will be in the water, including the water itself. So let me talk a little bit about solutions and dissolving things into water, and we'll go from there, okay? Okay, so this is section 4.1 and 4.2. Okay. Dissolving things in water. So water has the formula H2O. Sorry, hold on 1 second. There we go. And one way to draw water is like this, where you have the oxygen in the center and 2 hydrogens around it. More accurately, it is sort of an arrangement that looks like this. So here's the hydrogen atom right there. There's the other hydrogen atom, and then there's the oxygen atom. Okay, so H2O. It turns out H2O is capable of interacting very strongly with some materials. What happens is the oxygen atom has a negative charge, a small negative charge, and the hydrogen atoms have small positive charges. So I'm going to use this little delta sign to indicate that there are charges on this molecule, okay? So what happens in practice then is that water can attract itself through electrical interactions. So what will happen is the water molecule will essentially interact with other water molecules through electrostatic forces. So what I'm doing here is I'm drawing different water molecules interacting with each other. So notice the oxygen atoms, which are the center ones, the larger balls, they are interacting with the hydrogen atoms of other water molecules, and that's called hydrogen bonding. Okay, so hydrogen bonding is an example of intermolecular forces, different molecules interacting with each other. They're attracted to each other. But what happens is if you have certain types of ionic compounds, so for example, sodium chloride, the water molecule can interact with it. So this is table salt, right? Table salt, sodium chloride. What will happen is the water molecules will interact with the sodium ions and pull them away from the chloride ions, from each other. And instead of having one substance, NaCl, we now have two substances, Na plus and Cl minus. Okay, these are called ions. The AQ means dissolved in water. Okay, and essentially what happens is the sodium ion will form a relationship with the water molecules. So there's a water molecule. There's a water molecule. There's a water molecule. There's a water molecule. Okay, so those water molecules, the oxygen atoms are oriented toward the sodium ion. Opposite charges attract. You've probably heard that, right? The positive charge of the sodium ion is attracted to the negative charge of the oxygen atoms. Okay, I have explained why the oxygen atom has a negative charge and the hydrogens have positive. That's later in the course. We'll talk about that. Okay. Likewise, the chloride ion, which is negatively charged, is going to interact with the water molecules. But now it's going to interact with the positively charged hydrogen atoms. Okay. See how the hydrogen atoms are being drawn next to the chloride and the oxygens away, right? That's because the hydrogens are positively charged here. So we have these interactions here, okay? So the result of that is that many of these ionic compounds dissolve in water. Now, what is an ionic compound? Well, it's a compound made up of ions, charged particles. But in practice, what you can do is you can recognize that there are some common ions. So the first column of elements, group 1A, okay, there's your group 1A elements, right? These are metals, and they will all dissolve into water to form charges of +1. Just memorize that, +1. Second row, you have Mg. That's incorrect. It's Be, sorry. Be, Mg, Ca, Rb. Going a little bit faster. Sr, and then Ba. This is the group 2 elements. These are also metals, and they tend to form +2 charges. Okay, so when you look at these chemical formulas, if you see any of those elements in there and it asks you what species are going to be dissolved in the water, there you go. It's going to be those charges, Na plus, Rb plus, Sr plus 2 or 2 plus, Mg 2 plus, that's so forth and so on. Now there's a few others that I want to go over. These are what are called the transition metals, starting with scandium. Oops, I drew this too high. It's got 10 columns. It starts in element 21, which is scandium, and goes all the way to element 30, which is zinc. And zinc is one I want to point out. I'm going to circle that one. And then below the next row, it comes here and you've got cadmiums right here. But next to it is silver, Ag. And I'm going to circle that one. And then in the second row, I'm sorry, the third row, which is right here, you have Al. I'm going to circle that one. Okay, so there's Al. So this is group 3A. And aluminum is one of these three that I'm circling. So now in group 4A, 5A, 6A, and 7A, what you see is you have, let me draw these in here, boron, carbon, nitrogen, oxygen, fluorine. aluminum, silicon, phosphorus, sulfur, and chlorine. Okay, and now I'm just going to draw in the bromine and the iodine. These form -1 charges, these form -2, these form -3. And then aluminum, zinc, and silver, those are 3 you want to memorize. Aluminum, I'll write them down here, is +3. Zinc is +2. And silver is +1. So AZA, right? There's like a little pattern there. And the charges, look how the charges go, 3, 2, 1. Okay. So group 7A, -1, 6A, -2, 5A, -3. The 3 elements there in the middle, aluminum, zinc, and silver, +3, +2, +1. And then group 1A +1 and group 2A +2. Okay. So many of the other ions outside of those can be figured out by knowing one. So for example, if sodium is combined with another ion, you know sodium's +1, so you can mathematically figure out what the other one is. Okay, so that's the idea. Ionic compounds dissolve in water and they form ions. Okay, now molecular compounds are very different. Molecular compounds do not generally behave like ionic compounds. They don't form ions. They may dissolve in water. So some molecular compounds dissolve in water, but many do not. So how do you tell which ones do and which ones don't? We just have to kind of memorize them, to be honest with you. This is where you just get into the personality of these substances. Okay. So what dissolves? So let's do molecular compounds. Which ones dissolve in water? Which ones don't dissolve in water? Man, it's tricky. One is acids dissolve in water. So generally, an acid can be recognized in that it has some number of hydrogens in the formula, and then it has nonmetals. So for example, HCl. That would be an example of an acid. So see how it has the H first? Okay. So if you look at the formula and it says H and then something else, there's a good chance it's an acid. Okay. Another example, H2SO4. See, it's got the hydrogen and then SO4. That's most likely an acid. Acids generally dissolve into water. Okay. Another example, H3PO4. There's your hydrogen first and then PO4. So that's probably an acid, and it is. Okay. Then you also have these things called bases. And they dissolve into water. I'm going to put in parentheses N for nitrogen. These are the bases that have nitrogen in them. And I'm just going to list them out. NH3, CH3NH2, C6H5NH2. So if you see a chemical formula and it's either NH3 or it's NH or NH2, and then it has some number of carbons, that's most likely what's called a nitrogen base. Those are important in things like DNA and proteins. And those dissolve into water as well. Okay. So these dissolve. You've also got sugars that dissolve. So sugars are very, very different. They're just very different. You really have to go into more advanced chemistry to understand what they are. You cover them in a lot of biology courses. So sugars are typically what they are rings that have OHs off of them. Okay. So here's an OH and an H. Here's an H and an OH. Here's an OH and an H. OH and an H. OH and an H. So when they are rings and they have OHs off of them, that's typically what we would call a sugar. And again, there's different types. We can't be too definitive about it. But if you see a molecule with a bunch of OHs, it's probably a sugar, and they dissolve into water. And then you have alcohols. So alcohols also have OH. So, but they tend to have one, maybe two. But generally one OH. A glycol has two, but a glycol is a sort of alcohol. Okay, so those are alcohols. They also dissolve into water. Most other molecular substances do not dissolve into water. Okay, so if they dissolve, the question is, do they form ions? And the answer is not here, no ions. Not here, no ions. Yes, they do form ions here. And yes, they do form ions here. Here, the ions they form is H+. Here, the ions they form is OH-. And we'll talk much more about those when we get to acids and bases. Okay, those are molecular compounds. So you may have something that doesn't have any of those. So for example, it might be NO2. Okay, that's a molecular compound. Does it dissolve? Does not dissolve. It's not an acid, it's not a base, doesn't follow those criteria. See, it doesn't have NH, right? Or NH2 or NH3, it's just NO2. It's not a sugar, clearly, it doesn't have any carbons in it, doesn't have any OHs in it. It's not an alcohol. So it's molecular. It's just two nonmetals, so that's molecular, but it doesn't dissolve. So in general, these are the ones that dissolve into water. Okay, but they don't, well, actually, these two form ions. These two do not. Okay, so you want to memorize those. Memorize the acid, the base, the sugar, the alcohol. Sugars and alcohols dissolve, but they don't form ions. Acids and bases do dissolve, and they do form ions. The acids form H+, and the bases form OH-. Okay. So let's come back to that problem, and we'll go through it. Okay, take a look at the first one. Now, this is called isopropanol. Now, they're tricking you here. I think it's kind of mean in a way. They don't show you an OH in here. So what they're expecting you to do is to recognize, oh yeah, you have the carbons and hydrogens. It's the ending. So in chemistry, when something ends in OL, all, it's generally an alcohol. So isopropanol is an alcohol. So what do you get when you dissolve isopropanol into water? It does dissolve, right? Because it is an alcohol, but you don't get any ions. So for this first one, all you would need to do is draw this formula again, because it's not going to break up into ions. So you just draw the formula, C3H8O, and then put a comma, and then you want to put water in there, because if it's in water, water is in the water. So C3H8O and then comma H2O. Sucrose. Now again, they're not showing you the whole structure of this like I did. They're just giving you the formula, and you may not be able to recognize that that's a sugar. So how do we tell it's a sugar? It's the ending, OSE. Ribose, sucrose, glucose, dextrose. Look in the ingredients of sugars, of sweeteners. Many of them, most of them are what we call oses, so hexoses or pentoses. So sucrose is actually two rings connected together. I'm not going to go through it. You can look it up. But this is an ose, so it's an alcohol. So again, you just write the chemical formula, comma, chemical formula for water, which is H2O. Those are both molecular substances, molecular compounds. Nitrous oxide, N2O. Okay, so go through it. Is it an acid? No, it doesn't have that hydrogen in the front. Is it a base? No, it doesn't have N with H's attached to it. So it's not a base. It's not an alcohol, doesn't have carbon. It's not a sugar, doesn't have carbon. But there's no metals in there, so it must be a molecular substance. So then what you would do is you would just say, okay, well, if that's the case, it doesn't dissolve in water. If it doesn't dissolve in water, you don't write it. So here, the only thing present would be water, H2O. Okay. Let's look at another one. Again, here's your alcohol. This is actually the same alcohol, kind of lazy. C3H8O. Okay, so you would write the chemical formula for the alcohol and then comma water, right? Alcohol is dissolved, but so dissolving, you're writing the formula here because it dissolves in the water, but it doesn't form ions. Finally, here's one that's actually an ion. I'm going to come back to that one. This one, acetone, again, okay, so this is when it ends in O-N-E, that's called a ketone. Ketones do dissolve in water in general, but they don't form ions. So same thing, you would write the chemical formula, comma, H2O. Okay, so you have alcohols, which end in OL. You have sugars, which end in OSE. And then you have ketones, which end in ONE. All three of those dissolve in the water, so you would write their chemical formula down, but you wouldn't write them as ions because they don't form ions. They're non-ionic. They are molecular substances. Now, this one right here is a little tricky because this metal here, iron 2, and then the non-metal is a polyatomic ion, and I haven't discussed polyatomic ions. I have a lot of videos on polyatomic ions, but let me go over this a little bit, and then we can look at it, and then we'll move on to the next one. Okay. Polyatomic ions are ions. Okay, so this one is FeSO4. That's the chemical formula. It's called iron 2 sulfate. Okay, now when you look at, let me see if I have this here. Doesn't look like I have this here, but let me check one more time. There we go. When you look at the transition metals, so I'm going to write out just the first row of the transition metals. So this is group 3B, which is scandium. And then next to it is 4B. I'm using the older system, but the older system is useful. Titanium, 5B. I'm not going to write out the Roman numeral for all of them. Vanadium, then chromium, then manganese, then iron. So here's the iron. That's the one we need here. Cobalt, nickel, copper, and zinc. Okay. Those are your transition metals. That's the first row of them, right? There's more than that. Okay. So here's what happens. The charges we figure out from the name. The name is how you figure out the charge of the metal. Since it's called iron 2, they're telling you the charge is Fe2 plus, right? So there's the symbol Fe for iron, ferrum. And then there's the charge, which is +2. So there's your charge of the iron. Now, you may not know what sulfate is, so let me give you a few of the polyatomic ions. Sulfate, phosphate, carbonate, hydroxide. Okay, there's 4. SO4 2 minus, PO4 3 minus, CO3 2 minus, OH minus. There's just 4 of them right there. There's many of them out there. You can look them up. Those are called polyatomic ions. So here's what you do. They told you it's Fe plus 2, and then you got SO4 minus 2. That's the sulfate. So that means that for this substance, what's going to happen is you're going to get iron 2 and then sulfate in the water, and then you also have water. Okay, so notice if it's a metal with a nonmetal, that's an ionic compound, you break it up into the ions, right? So ionic compounds form ions. That's why they're called ionic compounds. They break up into ions in the water. So in this case, instead of just having 2 substances like you would with a molecular compound, the ionic compounds give you an extra one because it breaks the compound into 2 parts. It's kind of cool. It's the water that's doing that, right? The water is pulling those ions apart. And again, you can watch videos on that one. Okay. So for that one, then you've got again, you've got two that are molecular substances where you're just going to have two answers. You're going to have water, H2O, and then you're going to have the chemical formula. But this one, you're going to have three. You're going to have the iron +2 and the sulfate -2, and then the water, H2O. Okay. I'm just looking to see if there's any that are significantly different. This one right here, well, we already did acetone, right? That's a ketone, that's soluble. So you're just going to have the formula and the formula for water. Here's an ionic compound. K is potassium. First column, metals. So metals, metals, metals. Aluminum's a metal. And then these are the nonmetals over here on the far right. Okay. So metal, nonmetal, metal, nonmetal. So you're going to get three species there. You're going to get the copper, you're going to get the chloride, and you're going to get the H2O. You're going to get the potassium, you're going to get the cyanide, and you're going to get the H2O. Okay. So there you go. That is an example of making predictions of the species. Okay, the next thing I want to do, and again, there's other videos on this that you can watch, some with even more detail. The next thing I want to do is I want to do writing net ionic equations. Okay, so this is an important step in terms of dealing with precipitation reactions. Okay, so it says here the following, oops, sorry, let me share this one. The following chemical, so this is writing net ionic equations. The following chemical reaction takes place in aqueous solution. So here's the equation. Now, technically speaking, they're not wording that quite right. Really what if they want to be technically correct, what they would say is the following chemical equation represents the chemical reaction. Because remember, a chemical equation isn't the reaction itself. It's a mental construct we have to describe what we're observing in nature, right? There's a reality that we exist in. We're trying to describe that reality through this equation, right? So the equation is describing the reaction. Shouldn't really call that a reaction. We should call it an equation. So 2AgF aqueous dissolved in water plus K2S aqueous dissolved in water goes to Ag2S solid plus 2KF aqueous, right? So you're getting a solid there. That's what a precipitation reaction is. It's where you form a solid in water, okay? Precipitate in chemistry means solid formation. Precipitate in meteorology means rain, like liquid or solid, right? Snow is precipitation, hail is precipitation, rain is precipitation. But in chemistry, the formation of a solid is precipitation. You can observe precipitation when you see the water change color and you can see little particles in there. It starts to get cloudy, or you actually see really particles falling down to the bottom or floating at the top or just suspended, right? That's what a precipitation reaction is. When that happens, when you go from having something that allows light to pass through it to now it doesn't allow light to pass through it, that's called precipitation. Okay, write the net ionic equation for this. So now, really what you're going to do here is you're going to go through several steps, and I want to show you those steps in the remainder of the meeting here. I want to show you how to write net ionic equations for precipitation reactions. Okay. And again, there are many videos that I've made on this, but I think it is useful. I think it is useful to see multiple examples. So let's go over this one. Okay. So they gave you the balanced equation. By the way, sometimes people put a space between the coefficient and the chemical formula, but some people don't. I generally don't, but they do on ALEKS. Okay, so there's the equation. How are we going to write the net ionic equation? There's several steps in this, so let me go through it. The first thing you do, I would recommend pulling out the table, is you try to figure out what the charges of these ions are. So this is an ionic compound. How do I know it? It's got a metal and a nonmetal. That's ionic. This is ionic. It has a metal and a nonmetal. Now, how do you know what a metal and a nonmetal is? Well, it kind of depends on the periodic table you're using. But the first two columns are metals. All of these in the center are metals. And then when you get past the center, aluminum is a metal, okay? And this row down here, tin, element number 50 is a metal. Thallium, 81. Lead, 82. Bismuth, 83. Polonium, 84. Those are all metals. So generally, you can think of the metals as everything that goes right to this staircase. See, they have a staircase. You see this right here? There's a staircase right there. And that staircase sort of borders the metals and the nonmetals. The elements next to the staircase sometimes have in-between properties. They're called metalloids. They're in between. But if it's to the left, it's pretty much, if it's to the left of that staircase, it's a metal. These are metals down here too. So they've done a color coding system here, which is maybe good, maybe bad. But everything over here to the staircase is a metal. And then these are metals as well. So most of the periodic table is metals, right? Okay, so you look them up. Remember, there were three that I said to memorize: aluminum +3, zinc +2, and silver +1. So here's what I'm going to do. I'm going to say, look, there's Ag, so that must be Ag plus. And then we said, oh, fluorine, where is that? Oh, there it is. It's in group 7A. That's -1. Everything in that column is -1. So it's Ag plus and F minus. Okay, I'm not putting the states of matter yet. We'll come back to that. Then we have the second one, K2S. So you got K right here. That's group 1A +1. S, group 6A, that's -2, right? +1, +2, -1, -2, -3. So you got S2 minus. This is telling you the charges. Don't worry how many there are yet. We'll come do that in a moment. And then, oh, I forgot the K. I'm sorry. Now, see where it says solid? I'm just going to write it exactly like it is. And I'll put the S there to remind myself that's solid. A precipitation, what happens is, in a precipitation reaction, you form a solid. And that's the solid that gets formed right there. So we're going to write the chemical formula for the solid. Anywhere where it says aqueous, we break them up into ions. So K is plus and F is minus. Right? Again, first column +1, 7A column or 17 in the other system is F minus, that'd be -1. Okay? So the format of this equation should look like this. Anything that says aqueous should have two things now. See how this is aqueous? It now has two separate things. This one's aqueous, so two separate things. If it says solid, it's just going to be one thing. Again, aqueous, so two separate things. If it has a charge, if you separated it, write aqueous next to it. Anything you separated, write aqueous, because that's really what the separation is. It's saying that it's dissolved in water, so it's aqueous. Okay? Now let's go back and do the numbers. There's more than one of some of them. This 2 refers to the silver and the fluoride, to both of them. So 2 and 2. There's only a 1 here, so we don't need to put any numbers here. There's a 1 there, that's cool, but there's a 2 here, so 2 and 2. The 2 refers to the whole formula. So if you break 2 KFs, you're going to get 2 K pluses and 2 F minuses. That is now called the complete ionic equation. Okay, or total ionic equation, or ionic equation. Different names depending on who you're talking to. Sorry about that. The last thing we want to do is we want to get the net ionic equation. So this is referred to as the molecular equation, just to remind you. It's balanced. Now we're going to do the net ionic equation. For the net ionic equation, here's what you can do. This is only one approach, but it's the one I use. Think of algebra mathematics, right? 3x plus 17 equals 4y plus 17. What can you do algebraically to simplify that equation? You could subtract 17 from both sides, right? Or in layman's terms, cancel 17. Of course, that's not, not technically correct to write it to say that. We're not canceling anything. But what we're doing is we're recognizing that if 3x plus 17 is equal to 4y plus 17, it has to be the case that 3x is equal to 4y because the 17s are identical on both sides. Let's do the same thing for a chemical equation here. If you see something with the same number of them, the same charge, the same symbol, and the same state of matter, all of that has to be the same. So aqueous and solid, no, you can't cancel them. 2 of them and 1 of them, you could cancel 1, but you can't cancel both. One's negatively charged, one's not charged, you can't cancel them. But if everything is the same, the charge, the number of them, the symbol, and the state of matter, you can cancel them. So 2F minus, 2F minus, K. Oh, did I have a 2 here? I'm sorry, there's a 2 there. 2K plus aqueous, 2K plus aqueous. I hope you caught that before I did. So what's left now? I canceled a bunch of stuff. The only thing that's left is 2Ag plus. We can't cancel the Ag. The S is still there, S2 minus. And then that gives you Ag2F solid. So this is called the net ionic equation. We've canceled or simplified it by noting that the K plus and the F minus did not change from the left to the right, from the reactant to the product side. So there's no need to have them in the equation at all. So we call this the net ionic equation, okay? So precipitation reaction, you're getting a solid. It's telling us that the solid formation is coming from the silver ion and the sulfide ion. Silver plus sulfide gives you silver sulfide, which is a precipitate in water. And what does that mean? Does not dissolve in water. That's the precipitation part. KF dissolves in water. K2S dissolves in water. AGF dissolves in water. How do I know? They're all aqueous. If they're all aqueous, they dissolve in water. But this one's a solid in this equation. So that means it does not dissolve in water. Okay, let's look at one more example. Okay, I'm going to write the molecular equation again. So it's 2Fe NO32 plus 3Na2S goes to Fe2 S3 solid plus 6NaNO3 aqueous. Okay, that's the molecular equation. And it's balanced. You can tell it's balanced, right? Check on it. Is the same number of iron atoms on both sides? Same number of nitrates on both sides, same number of sodiums on both sides, and same number of sulfurs on both sides. Now let's do the complete or total or ionic equation, complete ionic equation. Don't worry about the coefficients yet. We'll come back to them. You have iron, but we don't know the charge. I'm so sorry, but we don't know the charge for sure. So this is where what you want to do is have a table of polyatomic ions available. You can Google them, just Google polyatomic ions. And what you'll find is that NO3 is called the nitrate ion. There it is, and it's NO3 -1. Now, how many, by the way, it looks like I wrote this wrong. This is a 3 here. So let me just check, make sure I got everything else correct. It looks like I did. It's aqueous. So we're going to break it up into the iron and the nitrate. Now, how do I figure out the charge of the iron? We can't memorize these here. There's nothing to memorize except for silver, zinc, and aluminum. The other ones, you can't memorize them. So what you got to do is you got to figure out the metal from the non-metal. The nitrate ion is negative, right? How many are there in the formula? So let me write a little circle around that. There's 3 nitrates. That's the 3. That means there's 3 of the nitrates in there. If each one is -1 and there's 3 of them, that's -3. So the iron has to be +3. Okay. Now let's go back and figure out how many there are. You've got a 2 in front of here, so you have 2 irons. But you also have this 3 after the nitrates. So 3 nitrates, but then you got 2 of the whole thing, right? So it's really just to show you 2FeNO3 really means FeNO3, NO3. That's FeNO3. But you've got you got 2 of them, so you just have a second one. That's really what that means. So how many irons do you have? 1, 2. How many nitrates do you have? 1, 2, 3, 4, 5, 6. So you got 6 of these. Okay. Now let's do the second one. Again, put a plus sign next to it. We're adding these together. They're separated. So we got 3Na2S. Okay. So Na, first column, +1. Sulfur, that's over here, group 6A, -2. Okay. How many sodiums are there? Well, it looks like there's 2 of them, but then you've got the 3 in front. So it's 3 times 2, you got 6. You got 3 sulfurs. Okay. Notice 6 pluses and 3 -2s are going to cancel because 3 -2s is -6. Again, anything that has a charge is aqueous. Ions, we call them. Now, on the product side, this is the solid. That's the precipitate. That's the product of the reaction that we're interested in. So that one, we're just going to write it just the way it is. No need to change it. And then the last one, you got 6 NAs. But they're plus because it's first column, and then 6 NO3s. Again, if it's aqueous, you write, or it's charged, you write aqueous. Okay, there's your complete ionic equation. Last step, cancel anything that's the same on both sides. 6 nitrates, 6, this is my funnest, to me, this is the funnest part. 6 sodiums, they cancel. So you're left with 2Fe3 plus aqueous plus 3S2 minus aqueous. And then you get Fe2S3 solid. So there's your net ionic equation. Okay, how's that look? Hopefully not too bad. Okay. Everything should be balanced in all three equations. You should have the same number of atoms of each element. The charges should add up to 0 on both sides. And everything should have a state of matter as well. Okay. Now, let's see here. I'm going to close that one. And let's do one more. Writing net ionic equations. The following chemical reaction takes place in aqueous solution. SnCl2 aqueous plus Na2S aqueous goes to SNS solid plus 2 NaCl aqueous. Write the net ionic equation for this reaction. Hopefully you can see that a little bit better there, right? Okay, so this is SnCl2. See how it says aqueous? That means you're going to break it up into ions. Aqueous, so that's the sodium sulfide. You'll break that into ions. Solid, you won't break that up into ions. And then NaCl, that's aqueous. You'll break that up into ions. Okay, so if it says aqueous, you break it up into ions. The format should be what we call a binary. For those of you that are computer science majors, right? Binary, zeros and ones, one or the other, right? It's either off or it's on. Same is true here. Binary means there's two parts: metal, non-metal, metal, non-metal, metal, non-metal, metal, non-metal. Binary ionic, right? Two ions, one's a metal, the other one is a non-metal. Okay. So let's take a look at this one. Okay, sorry, let me bring this over here. SnCl2. You know what I'm going to do? I'm going to try to do this. Hopefully that will work better. I'm going to put it in landscape mode. Hopefully that works better. So SnCl2 aqueous plus Na2S aqueous goes to SNS solid 2 NaCl aqueous. Okay, write the net ionic equation. Okay, so when you look over here, surprising to me a little bit, I would expect tin, element number 50. It is a metal. It's not transition metal. It's what's called a post-transition metal. I would have expected that it would have a charge that you could very easily predict, but it turns out it has variable charges, just like the transition elements do. So it could be +2 or it could be +4. It has different possibilities. So what we're going to do is we're going to come over to the chloride. Chloride is in group 7A. Right? Element number 17, chlorine, group 7A. 7A is -1. So we now know that it's, okay, we don't know what SN is, but we know the chlorine is -1. How many chlorines are there? There's 2. Now let's figure out the charge of the tin from the chloride, from the chlorine, okay? 2 -1s is -2. So the tin's got to be +2. Okay. They are aqueous, so we're going to write aqueous here. The ions are always aqueous in water. Second one, sodium. Now that one, hopefully you know sodium already, right? In fact, I'm going to put a 2 there because I'm doing it more quickly, right? That means there's 2 sodiums, but the charge is over here. +1, group 1A. Sulfur, group 6A. So that's -2. And then I just kind of naturally put aqueous because, you know, it's telling you the compound is aqueous. There's your precipitate. Precipitate. S and S solid. There's your sodium and your chloride. Hopefully you recognize quickly sodium's +1, chloride is -1, group 1A and 7A. A little tip about precipitation reactions. If you do see that it's a precipitation reaction, the charges don't change. By the way, there's 2 of everything, so 2. Meaning if you know it's Na plus over here, it's got to be Na plus here. It's not going to be Na plus on the left and then Na something else on the right. When we do redox reactions, which is section 4.4, then we have to be concerned with changes in charges. But for right now, if we recognize, you know, one way to recognize it is aqueous plus aqueous gives you solid and aqueous. That tells you it's good chance it's a precipitation reaction. Okay. There's your total ionic equation. Now we're going to get rid of everything that is exactly the same on both sides, which would be the chlorides and the sodiums. By the way, the ones that we cancel, there's actually a name for them. They're called spectator ions. So in this problem, if you had a question where they said, identify the spectator ions, it would be Na plus and Cl minus, sodium ions and chloride ions, okay? Spectator meaning that they're watching, but they're not involved. And technically that's not true, they are involved, but to the most kind of casual observer, we might say, it appears as though they're not involved in the reaction, okay? So what's left over? You got the tin, and then you got the sulfide. And then your product is SNS, solid. Tin, 2, sulfide. By the way, there is a system. It's an older system, but we still do use it, of ic and us. I'll write it this way, us and ic. So if a metal has 2 or more possible charges, the one that's more positive, you name the metal with ic at the ending. If it's the most positive charge, I'm sorry, the least positive charge, then you end it with OUS, us. So for example, suppose I had these 2 ions. Which one's more positive? This one right here. So we would call it stanic ion. It doesn't have the chloride in it, right? It just has the Sn+4. So stanic ion. Really, it's a cation. So let's write cation. This is the stanic cation. The one that's less positive, okay, less positive, this one ends in OUS. So that's called the stannous cation. It's an old system, but it's still in use. Let me show you one more example. Okay, this one's more positive. So it ends in ic. So it's called the ferric cation. See how I'm using the Latinized names? I'm not calling it iron, so it's not called ionic. You could call it iron 3. So that's how we would say it in English, but if we want to use the older system, the Latin system, we would call it the ferric cation. Ic if it's more positive, us if it's less positive. So this is less positive. So ferrous cation, which I think is cool, especially as I get older. But another way to do it is just called iron 2, right? Iron 2, Fe is iron, and then 2 refers to the charge. Remember that when you use these Roman numerals, that's telling you what the charge is. So +1 is written as 1, +2 is written as 2, right? Actually, these are called Arabic numbers, and these are called Roman numbers or Roman numerals, right? +3, +4. So there's your Arabic number. There's your Roman numeral. You can keep on going as much as you want, right? I've never seen anything beyond 7. Actually, I guess I have seen something beyond 6, but 7 is the most I've seen it. So the Arabic is +7. The Roman is VII, right? V is 5, I is 1, so 5, 6, 7, right? You're counting essentially. Okay. So there you go. So there's that system. There's those kinds of net ionic equations. Again, the polyatomic ions, what I would recommend doing is just pull up a table of polyatomic ions. You can just Google polyatomic ions. You make a flashcard with most of them or all of them on your flashcard and just have them next to you. When you write the flashcard, have the name, and then next to it, write the chemical formula. So like, for example, phosphate, right? PO4 3-, right? Yeah, charge is important, right? The thing about precipitation reactions is all about the charge. We're making sure that things are charged. That's how this is all occurring. In the end, ultimately in chemistry, really what's happening is charges are interacting with each other. Charged particles attract each other. If they're the same charge, they repel. But if they're opposite charges, they attract. So a lot of really what's happening in chemistry fundamentally is this attraction due to charges. Ions are attracted to each other. But if the ions are attracted to each other, why can the water pull it apart? Well, because the water itself is charged. So the water, its charges overcome the attraction of the ions for each other and pull them apart. There's kinetic energy associated with it as well, and that's a part of it. But the point is essentially that charge is an important aspect of it. Okay, so enjoy. My next lecture should be on acid-base reactions. So I'm going to spend the day talking about acid-base reactions, and then I'll get into the redox reactions and then concentration. So take care. Have a great day.